cooking, right?
But it does have some internet.
Hello, hello. Yet, is it going through? No?
Is it on?
I don't know. I just put it.
Oh yeah, it's on.
I have no idea how to use it.
Okay, let's just go ahead, I guess.
All right. So we start?
So welcome everyone. Thanks for coming. So here we have Ivan talking about how JavaScript application work inside the browser. So if you're interested in any browser, in presenting a browser, come talk to me, Jordan, Ashik, or Karen, so we can arrange one. And please feel free to ask Ivan any questions during the browser, because we have some GitHub stickers and other prizes to give away. And let's get started.
Yep, let's start. So, hi guys, as you already know, my name is Ivan. I'm a developer from the Hyperion crew. And I had really hard time coming up with a name for this talk because you want it to be attractable for the people, so more people come, but I failed. So what you see on the screen is what you get. It's quite simple. It's going to be just about the JavaScript and its native environment browser. So majority of the people here works with the JavaScript day to day. So some of the things you'll definitely know. Some of the things you may intuitively understand, but couldn't really explain why it works the way it works. And hopefully some of the things are going to be completely new, or otherwise I just waste your time. So let's start. Do you click or? Yep. So today's agenda is we're going to start with the event loop. Then we're going to talk about the concept of the task in the JavaScript. Then we'll discuss what task sources and task queues exist and why they were introduced. After that, we'll talk about the concept of the micro tasks. And finally, we'll discuss what is idle callbacks and why they are required. And finally, we talk about the render because it's browser, right? All we do to render something to the users, for the users. And as I talk, I'll show you a lot of examples because I don't want you to guys fall asleep while you're having your lunch. So our journey starts with the event loop. And what event loop is, it's just a while loop during which the task is being executed and then the render being done. And task is just a piece of JavaScript code, while render is repainting of the user interface. And that's it, if you oversimplify that. But why it's important for the JavaScript? Because it's representing the concurrency model of the JavaScript. As you all know, there are no threads or interrupts in the JavaScript, right? So with JavaScript, we can only do one thing at a time. And which is not really true, but we'll come to that. And if browser needs to respond to the user interactions or the API callbacks, it needs to somehow juggle the tasks and prioritize them. So your event loop isn't blocked. So what blocking is, and I'm pretty sure you all seen blocking at least once. That's when page is just frozen. And we are all on the same page about that. So this is just dumb animation I came up with. It doesn't really matter. It doesn't do anything helpful. But I like thinking about the event loop as a heartbeat. With every beat, it does one task and one render, potentially. And it's keep happening again and again. By the time it's blocked. So as you see on the click of the button, we call the alert function, which is synchronous. And that's where your heart just stops. And your page is dead. It's not being working anymore till you release it. And yeah, that's all I wanted to share with you about the blocking. So I keep saying task, but what task is? As I said, it's just a function and nothing else. And if you think about the nature of any function or any code, it can be either bound by the CPU, such as like parsing of the JSON or iterating through the arrays, no matter which function you use, or calculation of the hashes, or maybe transformation of the binary data, like transforming SVG to PNG in JavaScript, right? That's also a CPU-bound task. And other tasks, they are bound by some input-output, such as network, or hard drive, or user interactions. And IO-bound tasks, they are slow by their nature because they are being done outside of your control. So you can't really make it faster no matter how quick your CPU is. But And they could block event loop because they're naturally slow. But because browser has a concept of the web API, it's not happening. So what is browser web API? You might, at least when I hear the web API, I might think that this is just HTTP call, the first thing that comes to my mind. But that's not limited to that. So all the functions that are bound not by the CPU are being implemented by the browser normally. And the mechanism that makes that work together is called callbacks. And what callbacks is? Callbacks is just one function that accepts another function as a parameter. And then when the first function is finished, it just calls the first function back, the injected function back. So let's take a look at some examples. So this is just another dumb piece of code. I'm terrible in creativity, so there's no real upline for this code. It's just an example. And in this example, you see two functions that are not bound by the CPU. One is set timeout, so it's definitely not bound by the CPU. And one is subscription for the button click, so listening for that event. This is another function that is not being bound by the CPU. You can't really say probably this is IO bound tasks. These are IO bound tasks because there is no real input, maybe from the user only, but it's definitely not CPU bound task. And how many CPU bound tasks can you identify on this screen, guys? Any guesses? Well, maybe not guesses, maybe just know. No? How many CPU-bound tasks? If you split this code into the CPU-bound tasks, how many CPU-bound tasks could you identify here? Different types of those. Sorry? You're close, but I'd say 3, because you probably missed the top-level task. So the first top-level task where it all starts, it declares the function, it registers the handler for the button click, and then it executes the function. And then we have two asynchronous web APIs. One is the set timeout, and one is the button click. Sorry, and callbacks for those APIs are to another tasks that are bound by the CPU. All clear so far? Any questions? No? All good, cool. So this is all kind of too abstract. So I want to show you the tool called Loop. It was done by Philip Roberts, and I highly encourage you to go and watch his talk. He has a great talk about the JavaScript event loop. And this is the tool I'm talking about. And this is the same piece of code that I just showed you in the previous slides. On the left side, we have this piece of code. On the left bottom side, we have the click me button, which we'll be clicking on. On the right side, we have a call stack, which represents like where currently in the function your execution is, what's currently being executed. Then we have web APIs, which has the list of web APIs being used. And at the bottom, we have a callback queue. And callback queue is a structure that represents the queue of the tasks. So that's where whenever callback is being called, that callback is being put to the queue and then one by one picked up by the call stack. So if I save and run, you'll see that first top-level task is being executed. It registered the callback finished, it's being executed by the call stack. All clear, no blocking, all works nicely. But if I click on the button multiple times, what's going to happen, right? It's going to register multiple set timeouts. And after every timeout, it will put callback to the callback queue. And if the execution of the task is slow enough, other tasks will be just waiting. So let's see. I'll click 5 times. And though the first callback is already finished and 2 seconds already passed, you see it's not being executed by the call stack because it's waiting. It's waiting till its turn comes, right? And this is interesting thing that you'll see implications of this later on. I think it's being glitchy right now. Yeah, it's just being glitchy. Yeah, but this part is correct. Oops. Sorry. Oh my God. It should happen on stage, right? Cool. But you've got the idea, right? So even though the timeout is passed, it's not being executed immediately, though you as a developer might expect that it's going to be done exactly at the time where you expect it to be executed. Cool. So we are going to keep going. So this is how, according to the, this is how, according to the tool we just seen, this is how it looks. So you have event loop, you have task queue that has a lot of callbacks that are coming from some web API, and it just keep happening. But the problem is that some of the callbacks, they are naturally more important than others. For instance, user interactions. You know that users don't really like to wait when they click on the button. They like to see response immediately. And with this approach, browser doesn't really have any mechanism to prioritize one type of the tasks over another ones. And that's why it doesn't work like that in the real world. So this is how we come to the concept of the different task sources and different task queues. So according to the WhatWG specification, browser can have as many task queues and task sources as he likes to. And the only thing that is really guaranteed is the task sources that are the same, or the task sources that are put to the same task queue. They are going to be executed in the order. Everything else is not guaranteed. So if you have exactly the same situation, like over here, when you have 4 queues, one is user interaction queue, one is post-message queue, which is web workers. We don't really care what is that, just some different queue. Then we might have timers queue with intervals, timeouts, maybe set immediate, which is already obsolete. Or you might have potential web request queue with fetch and XHR in that. And if you have exactly this situation, browser might potentially pick up all 3 of user interactions and execute them one by one. Then it might see that there is timeout that is outstanding and take the timeout. Then it might do the post message. Then it might see that there is another interval that must be executed, and then pick up these 2. But this is just an example. How that works in the real life, there is no real way to know except to test it. And yeah, different browsers may behave differently, given that they have the same callbacks in the same queues. Maybe they don't even have the same queues, right? Cool. So any questions so far?
If I understood, so do you have access? I mean, do you control, or can you create different queues and different sources, or the browser?
It's a browser. So in the specification says that browser, any browser, it might have multiple queues. It must have multiple queues. So
then how can how does the browser group the things to put in?
that's up to specific browser. That's the problem. So the specification only comes up with the generic algorithm, while different browser might have their own scene of this, and they might implement it in their own way. You might get different results with the same code in the different browsers.
So a task queue would be that thing that you showed from the event loop.
This is the task queue. And all of these are task queues,
Yeah.
potentially.
So what is a task source?
So task source is like on click. It's one task source when user clicks on something. Or set timeout. It's also task source.
Or you mean
So
where
these
does the
are
task
examples of the task sources. So these are different types of the tasks. Depending on which web API they come from, it's a different type of the task. Cool. So this transforms our diagram into something like that, where you have multiple queues in the browser, right? And you have your web API that's pushing the callbacks to the different queues, and then by some unknown algorithm for us, a browser picks one, executes that, does the render, and it keeps happening all the time. But of course, this is not all of it. So what is the first thing that comes to your mind, guys, when you hear about asynchronous in JavaScript? Like first thing that comes to your mind? Async await?
Another processing different things in parallel.
But what concept in JavaScript comes to your mind? Sorry? API calls. But how do you enable all asynchronous in JavaScript? Promise? Yeah, that's the one I'm trying to push you to. But I expect that to come early, but that's fine. Yeah. So at least for me, this is promise. Whenever I hear about the asynchronous, it's promise. And async await, like behind this scene, I think they're using promises anyway. So yeah, it's promises. And after what we just discussed, you might think that promises just work the same way as other task works. And they potentially might have their own queue. And that's it. That's the way it works. But this is not the reality. Let's see one sample. Again, I'm terrible in creativity, so we just have button, the place to log text, and the function that logs some text. And in that function, we have two timeouts, one with 0 interval and one with 6 milliseconds interval. And at the end, we have a resolved promise that is also logging something to our called console. And if I click on the run multiple times, you will notice that the result is quite consistent. And our resolved promise always go first, no matter how many times I'm going to click. And this is because for the promises, browser is using concept of the microtask. And the word microtask, it presumes that this is the task that is really small. And therefore, what browser does, after every macro task, it takes the microtask queue and executes all the tasks in that queue. So what that means for us as developers, that means a few interesting things. So one thing is recursion. So if you have a recursive function that is being called without any exit condition, what's going to happen? It's going to freeze for a while, right? And then it's going to throw Stack Overflow exception. And then it's going to paint the user interface at once, which is kind of expectable, right? If we have function that is recursively calling set timeout, after what we just learned, we know that with every call of this function is going to push a new task to the queue, right? And in between, browser still can squeeze in the render. So it's not really blocking the user interface. There is no exit condition, but interface is responsive.
Sorry, what did you change with that?
I copied this and I call it instead of the recursive function. So it was with the recursive function before.
One has set timeout.
This one just recursively calls itself. This one recursively calls itself, but within of it, it's using set timeout. And the last one is recursive promise, and this is the worst case scenario. Because as we just learned, sorry?
It has to wait, then.
Yeah, so this is how it looks, right? Promise resolve, and then just console log. Error actually never going to be executed. And then I call it recursively, yeah. And when I click on the run, my interface will just freeze. And it's not going to throw Stack Overflow exception, because technically speaking, there is no Stack Overflow. It's just pushing a new microtask to the queue, right? And with every microtask, it keeps adding one more. So there is no way to reach render anymore. And at some point, browser will see that there is something wrong, and it will probably ask me to kill the page. I hope so. It should be. It's usually doing that. If you keep clicking on the UI. Yeah, finally, please kill it. Yep. But this is like interesting side effect of this approach, right? And it also raises a few other interesting questions. Like if you use not the native promises, but library like Q, or maybe some polyfills for the promises, is it going to work this way? I'd say no. I guess no, I didn't test that, but this is something for us to keep in mind, that there is it is kind of same promise, but it works differently, right? Any questions so far? I'll have water. Yep.
So in terms of micro tasks, is it safe to say that all browsers try to exhaust the micro task before?
They should be. They should be. That's what spec says. So what WG spec says that they should be keep going till it's empty. And if they don't do that, then they don't follow in the spec. That easy. But that's, again, if you're not using the native promise but something else, it might be different result, right?
One question even. So the browser freezes because I understand the queue basically it's growing.
It's not growing, right? So this is how it looks right now.
Yeah.
And with every microtask, it adds one to the end and finishes. Then browser checks, okay, is there anything else? And there is one more, and one more, and one more, and
So
that's
there's always like tasks like pending to be done. So that's why
Yeah.
it freezes. But then I guess like who is doing that work is one thread, right? I guess in the CPU.
So this is always one thread in the browser, and this is your thread, right? This is like your event loop, which is representing your thread in the JavaScript. Important part that only resolved or rejected promises are ending up in this microtask queue. So if promise in the pending state, it's not going to be there. It will wait till the API call is finished and then being put to that queue, because otherwise you'd be having this problem all over the place, right? Cool. Anything else? All good? We continue. Cool. So there are a few other things that worth mentioning, and one is idle callbacks. And what is idle callbacks? So idle callbacks, they were introduced so browser can perform the low priority work in the main event loop. And idle callbacks, they can skip multiple iterations of the event loop if there is no free CPU time. They might be safely called recursively. So the way this queue works, every time browser decides to execute idle callbacks, it sees what idle callbacks are currently in the queue and executes only them. It doesn't execute all those that were added after it started. So it's safe to do the recursion with these idle callbacks. Moreover, this is the pattern that they suggest us to use. I'll show you. Yep, same old UI you already seen. And I didn't remove timeouts. Let's just see how it works with the timeouts. And at the beginning, we have this request idle callback. And then we have another one after timeouts. And it accepts the deadline, which we'll discuss a little bit later. And then there is a promise. So if I click multiple times, and if I click long enough, you'll get all the possible combinations of the callbacks versus timeouts. So they might be in between, like you see in the first two runs. They might be in the start because there was some time to execute them in the first iteration of the event loop. And they might be split by the callbacks. If we scroll down, I hope to find something. Yeah, this is where they are at the end because probably there was no time to execute them previously. Yeah, but trust me, if you click long enough, you'll get all the possible combinations, except of the order of these callbacks is always going to be the same, and order of the timeouts is always going to be the same for the reasons we just discussed. Right, and the deadline. So the deadline object, it tells you how much time remained for you to finish the idle callback. Because if your one particular idle callback is too long, your browser event loop will still be blocked, right? It's same task. It won't be able to proceed. And if it takes like a few seconds, there's going to be no render for the few seconds. So if I run this and click on the run, you see it shows how many milliseconds left for me to execute. It's always usually going to be under 16 milliseconds for the reasons we'll discuss later. Cool. Any questions so far? Nope. Awesome. So now let's take a step back and talk about the last thing that left unchanged since we started, and that's render. So usually browser performs render up to 60 times per second, which gives us approximately 16.7 milliseconds for us to finish our job. Sorry. So if your task is longer than that, browser will start dropping frames. It's even less than 60 milliseconds because browser need to do actual render, which takes time. Browser need to do some internal things, which we don't care about. And there is also a microtask queue and idle callbacks, so it should be less. Ideally, like take 10 to 6, maybe 6 to 10, maybe even less. The less, the better. And what if your code is really fast? What if your task is really fast? Then browser might see that there is plenty of time left, and it might skip the render and do another task. So that's why I put the question mark, well, not here, but in the next one. So it's optional. There is not necessarily going to be a render with every event loop cycle. And for me, the best way to understand render is to see some animation, which we're going to do right now. So this is same animation already seen, but a bit nicer. And it is being done by the dumb set interval, which is just changing the scale of the button every 60 milliseconds. And looking at this, you might say, well, why not to do all animation like that? It's good enough, right? But this approach has few problems. And one of them is that it's really hard to synchronize this animation. So what I mean by synchronization? So imagine that you have multiple hearts, and they are using the same code, the same set interval to do the animation. And it works. You see they're beating the same. If I block the event loop, you'll see that it's blocking, all good. In the console, I'm logging all the callbacks. And right now, if I block the event loop, you'll see that they're still in the same order. So, sorry. So 0, 1, 2, 3. So all 4 hearts, they've done similar amount of callbacks for the last like 20 seconds. But if you leave this page opened for a while, you'll see how that slowly some of the hearts are becoming a bit faster than others, and some a bit slower. And this is because of the race condition of the web API. So sometimes some set intervals are just complete faster than others. And as time goes, this change just snowballs. If I pause even now, you see that the one is already changed the order with the others. And if I leave this for a long enough time, by the end of the presentation, you'll be able, I think you will be able to visually see that they actually beaten in the different tempo. Hopefully it's going to work. Sometimes it doesn't work that quickly, but we'll see. So what's the way to overcome that? Potentially, you may use set timeout instead of set interval. It's terrible advice, but because set timeout is not really one-off function, you need to call it recursively in order to achieve this animation. So you need to call it once, and then within the body, you need to call it, where is that? Sorry, I need to find that. I'm looking for the timeout. Sorry, where is the timeout? Where is the second one? It should be here. Ah, yeah, we start with this. So we start with start animation. Oh, so embarrassing. Give me a sec. Timeout. Is it the right link? Oh, you think so? Ah, right. Yeah. Oh, that's the wrong one. Yeah, that's the wrong one. Sorry. This is wrong. This is the wrong link. Sorry, I opened the wrong link. This one. So this is the previous example. That was the previous example. This is where you call it recursively. One set timeout and another set timeout within the function body. And this is going to work a bit more reliably because this is not one-off function. It's going to be called recursively, and there is less chance that this concurrency race is going to snowball. But again, this is a terrible example of how you shouldn't do the animation. And let's see if this is already different. Wow, it's still okay. Okay, we'll leave it. We'll leave it. So the first reason why it's bad is because it's getting out of sync, as we see on the first example. The second reason why it's bad is because set timeout and set interval, they are going to be executing even if you switch the tab. So they are going to eat your CPU and your memory, even if you in your battery, even if you are not on the tab. And you can't really predict the frame rate. So sometimes frame rate drops, though we still assume that it's 60 milliseconds because we need to put the interval into that function. And that's where you might fail again. So the right way to do that is to use request animation frame. And request animation frame was done specifically for the animations. That's where you can, before every render, browser sees if there is anything in the request animation frame queue. And if there is anything in that queue, it executes it in one go, but it doesn't execute those that were added during this process. So you can call request animation frame recursively and be sure that you will not miss any frames, and you will not be called your animation too quickly, less than amount of the frames that the browser does right now. That is more than amount of the frames. Does it make sense so far? Any questions? No? Good. So this is how your healthy frame might look. And it might have request animation callback, then do the task, then do the micro tasks, then wait for a while because there is nothing in the queues. Then it might do garbage collecting, then do the request animation frame queue, and then do the render. And some of the things are required, such as tasks, micro tasks, and the request animation frame. If there is anything in the queue, it's going to do it. And some of the things, such as idle callbacks, garbage collecting, or render, they're optional and depends on a few things. And so with this healthy frame, you're going to get 60 FPS, and all going to be running nice and smoothly. But if your code is slow, when things go south, you might get something like that, where your task is 60 milliseconds and your frame rate drops, so you get only 12 frames per second. And then browser does the micro tasks, animation frames, and render, and throwing out everything that is optional. It just tries to do the render as soon as possible. And typical example of this is when you have some slow on scroll handler. So you scroll down, there is some slow handler that responds to every scroll, and you see that the page is jerked. It's just not really smooth enough, and that's like typical example of such frame. Right. I just wondered if that's already visible or not. Maybe. So if you take a look at this, at the console, you see that there are already like 5 frames difference between some of the hearts. I don't think it's visually visible yet. Yeah, one is already ahead. But I wanna like, if you wait for 10 minutes, it's gonna be really out of sync. Right. So after what we just discussed, you might be dragged into the false feeling of confidence, where you think you know how it works and you feel safe. But the problem is that browser always have a wiggle room to maneuver, right? And we're used to the fact that like our CSS styles are broken, right, because of the different browsers. But sometimes differences are much more fundamental than that. And the last thing I want to show you today is one of these cases. Yeah, the similar animation that we've already seen, but this one is being animated by the request animation frame that we already seen. And did I show you the request animation frame? No? Oh my God, sorry for that. Let me quickly do that. That's sorry for this. So this is how you're supposed to do this animation if you really choose to. So you have function called request animation frame, and it accepts the callback. And in that callback, you get a timestamp, which is representing the high resolution of, like, timestamp with a really high resolution, which lets you calculate your step with a high precision. So you can, you should save how much time have passed since the last animation. You get the current timestamp, and then you can calculate how much you should move on your animation. And you call it recursively, and this is never going to get out of sync. And this is not going to be running on the background. It's going to be running with a really slow frame rate, but it's not going to eat as much CPU and as much battery as other approaches. Actually, even with set interval and set timeout, I think latest Chrome, it drops the rate of the callbacks, but other browsers don't do it, as far as I know. Maybe something changed recently.
And this happens before full render?
Before every render, regardless how much time passed since that's how you don't really tell browser how often you want to render. You just ask him to call you back when render is happening. Let's get back to our last example now. Oh, too early. So, yep, so this is done using request animation frame, the same code. This is done by the CSS, and this CSS is animating the scale using the transition animation. And this one is doing the same as this one, but instead of the scale, it changes the font size. And after what we just talked through, you might think that when I click on the button, it's just going to be blocking everything. But funny enough, one heart keeps beating. And you might like, oh, why, right? But for Chromium, it's kind of, I think the answer is because in Chromium, there's a concept of the compositor thread. And how compositor thread works, it makes the snapshot of the page, and it tries to identify which animation is safe to do outside of the main render. So any animation that doesn't change the positioning of the elements, it's safe to do outside of the main render. And because this one is doing repositioning, it's blocked, and this one is keep happening. So this is Chrome. Now let's go to the Firefox. So this is how WebKit works. It's not only Chrome. So any browser that is using the WebKit is going to be working like that. For the Firefox, I'm not sure which UI engine being used right now. It's using either Gecko or maybe Quantum right now. I'm not sure. It doesn't matter. But if I click on the button, oh, come on. But you see that the top heart is stopped, while these two, they keep going. And probably they found a way to do the layout recalculation in that separate thread. I don't really know why it's working like that. It's just an example of the different browser doing different things. Now let's go to Edge. Well, we haven't come to IE. We haven't come to IE yet, right?
It's gonna break, don't worry.
You think so? You think it's gonna break? No, you're gonna be surprised. Yeah, you're gonna be really surprised. At least I was like shocked. So I click on it, and this keeps happening, right? And you might, I don't know why. Maybe they found a way to do some kind of interrupting. Maybe the alert is just not really synchronous in the Chrome. But you see, it's much slower. It's kind of struggling to animate. But if I release it, it's going to be much smoother. Yeah, it's much smoother right now. So yeah, so 3 browsers, 3 different results. Let's go to IE. Yeah, the final boss.
Four hearts.
Oh yeah, it says that IE not supported. Okay, we'll go to read-only mode. That's fine. And this just doesn't work. I checked, there is no errors in console. I'm not sure what's wrong, but this is the same code that, surprise, surprise, doesn't work in IE. And if I click on the button, it's gonna keep animating. So probably it's similar to Edge in a way, but not really. But Edge is just superhero. It just works no matter what. Cool. So I don't have Safari, unfortunately, but you guys can come back to your Macs and check that yourself. So that's it. Thanks all for coming. Yeah. Any questions? Any last questions? No.
Is there some sort of real world example that prompted you to investigate these sort of things for personally, or?
It just weird things happening all the time, like in the real work. And the better you understand this, the easier to come up to the explanation and fix it. So I found this knowledge really helpful in my day-to-day work. That's the thing. And just wondering if it's gonna worse or not. Is it gonna get worse? Yeah, it's like crazily different right now. So yeah, don't do it like this. Yeah, I will. I will share the slides and links and everything so you can play around. Yeah, sure. I'll do that. Awesome. Thank you, guys.
Thanks everyone for coming. So I think we are planning another meetup at the end of this month, but we haven't publish it yet. So we will let you know when we are ready. And yeah, thanks, Ivan.
Thank you, guys. Thank you.
Last question. Eduardo, you want to speak? You want to speak?
Bevan won the sticker for answering the. It's hot here. It's so hot. Yeah. I feel really hot, damn it. Maybe just me getting nervous, but
Yeah.
Yeah, so what did you say?
Maybe you just play too much tennis.
I didn't play today. Yeah, sure. Maybe I played till 9.